Good morning and welcome to another week. What we're going to do today is talk a little bit about the machine, that is the mechanical ventilator. How does it function? What does it do for us? We're going to talk about some of those words that you had to define for last week, the phase variables, the things that go along with it. So the subtitle of this is All I Wanted to Know About Mechanical Ventilators, and you can add what we're afraid to ask. This is a picture of the old MA1. It was kind of a unique ventilator. If you needed anything on it for your IMV system or whatever, you had to be able to build it onto it because it didn't come with it. You also had to, after a while, if you wanted to set a respiratory rate of 12, actually let the machine breathe and time it for a minute, and then you would adjust your settings so that you got what you needed to at that particular point, which would have been your respiratory rate of 12. And then you could also measure your tidal volumes to see where you were. This is the Bear 3. We used to have these in the lab. They're not much more sophisticated. Actually, they are much more sophisticated than the MA1 was. This is a 1980s ventilator. You can see there's dials on this one that you can turn. Fairly accurate, worked out fairly well for us. It was a pretty good ventilator. We have the Puritan Bennett 7200, which is the big one there, and then the Puritan Bennett 840, which is the other picture. The newest Puritan Bennett is the 980, a little bit of a step up from the 840. Apparently there's one or two hospitals here, maybe in Tucson, that are starting to use that. It's an interesting one. I think they have loaded a program to where you may be able to take a look at that and see how that works. The Draeger 500 or 550 that a lot of the hospitals are using, we also have that program. That program is in your course content, or and if it's not there, it will be. But it'll give you a chance to take a look at it. The 7200, if you notice, it has a monitor on the side of it. That's where we would see our graphics, our waveforms, and then also told us a whole lot about what was going on with our patients for us. It was really quite a workhorse. It was also a generation of the 1980s and worked really well. Towards the end of the 1990s, that's when the Puritan Bennett 840 came into being. Interesting machine because it wasn't quite like some that we had used. So it took a little bit more to get used to it to figure out what was going on with it. This is a servo. This is a servo I. There's a new one out called the servo U, and I understand that Banner may be using those. I'm not quite sure about the VA. The last time the students were out there, they were actually using the Draeger. So how do the people decide what to change their vents to? A lot of it depends on how the vents are working. Are they working as they're supposed to? What's most effective? Is the company no longer supporting the ventilators? If they're not supporting the ventilators, if you need new ones, then you have to buy new ones. So a lot of times you'll see the reps coming around and they'll tell you exactly what's going on with the newer vents. If you notice on this one too, you can see the Conchotherm heater at that point. So we can use the Conchotherm on here. You can also see that there are some cylinders attached to this. So you could sometimes use this for transport, which is really kind of interesting. So we talk about ventilators for the most part. You need to remember a ventilator's a machine. That's exactly what it is. It is not an extremely smart machine. It doesn't talk to you, but it does yell at you when it alarms. It is a machine that has two basic parts. It has a part to take care of your PaCO2. It has a part that takes care of your oxygenation. When you're setting these machines up, you have to be able to set them up to take care of both of these parameters. Otherwise, things aren't going to work extremely well for your patient. So, pretty good definition of it, simply a machine to help or deliver breaths to a patient. There's four basic functions. You have to understand what this machine can do in order to be able to set it up to be able to be used. One of them is input power. Another is power transmission and conversion. Another is you have to have a control system, and then you have to have your output, and your output is where your waveforms and your graphics come into play. So you can use electricity for these. Remember, when you're using electricity for these ventilators, they have to be plugged into the red outlets. The red outlets are on the backup generator in case the electricity goes out. Some of the batteries that we have last up to an hour. They used to be about 30 minutes. Right now they're going up to an hour. We were listening to a presentation on the Puritan Bennett 980 on Friday. One of the things that they said at that point was the backup battery actually works for an hour, but if you have a second battery, as you get towards the end of that hour, you can go in and replace that battery and your ventilator will operate for another hour. Now, one of the things you want to be aware of is if you lose power, you need to go to your unit or wherever your vents are and make sure that the vents are actually working. The batteries do have to be charged, and the question comes up, how do you charge these batteries? And one of the things you do is you keep them plugged in. A lot of times we don't keep them plugged in. We don't know if the batteries are going to work until we start to use them. If the battery is not working, and unfortunately you do lose power, there's no way that this patient is going to be able to have breaths or anything else at that point. So always be aware of that. Pneumatic, these are your ones that use gas. During the year 2000 changeover, a company called Vortran came out with some pneumatic ventilators, transport type ventilators. These are really, really good because you can use them for transport or in the MRI suite. As a result of that, the hospitals still have some of those, and on occasions they're able to use them if they need to. Both of these actually have microprocessors in them, circuit boards. You need to be careful and make sure that if you're setting up a heater, that you don't flood the circuit board. The second thing you want to watch out for is what can you and what can't you do with the ventilator. When we had the Puritan Bennett 840, they did not have a container or unit on it that allowed us to give treatments off the ventilator. We had to give them off of the wall on the flow meters. One of the things we found out early on was if you were going to give a treatment, you had to keep the flow down to about 2 to 3 liters. Otherwise, we had terrible problems with our alarms. We had problems with measuring the tidal volumes and different things along that line. We actually had a therapist that was told to do that. The therapist chose not to, set the flow meter at about 7 to 8 liters, and ended up actually destroying a lot of the circuit boards. And of course, the ventilator stopped working and the ventilator had to be changed out. So just a really quick memory check. You should know how to do this, okay? All of the following are functions of mechanical ventilation except you have turbo power, input power, power transmission and conversion, and control system. So that's a cool one. So power transmission and conversion, this is your drive and output control mechanisms. Drive is the force you need to deliver this gas under pressure. How much resistance and compliance are we working against? And that's what we're going to start talking about this week is compliance and resistance. And basically with output control, it's actually one or more valves regulating the gas flow to the patient. How do they work? There's probably about 4 or 5 of them. You'll probably talk a little bit about those in 5th semester. The drive mechanism, there it is. It has to convert that input power to useful work. And it's going to influence your flow and pressure patterns. It can be a direct application or indirect application, just how the vent is put together. The output control valve, it regulates the flow of gas to the patient, and it can shape your output waveform or your graphic that goes with it. And these, for the most part, pneumatic diaphragm, electromagnetic poppet or plunger valve, and a proportional valve. Control circuit, it manipulates your pressure, your volume, and your flow. One of the things that you're going to see when we start talking about the rest of this is everything is time or actually works off of pressure, volume, flow, and time. And so if anybody ever should ask you, what are the controls and the control circuits? Who operates them? Well, it's pressure, volume, flow, or time at that particular time. So the control circuit, for the most part, is a system of components. They measure direct ventilator output. They can either be replacing the patient's breath or they can assist the patient's breathing effort. So this is your control. This is your assist control, SIMV, IMV. And it can use mechanical, pneumatic, electric, electronic, fluidics, either together in combination with each other. And that's all you really need to know about that. So here's your memory check for this one. Control circuits may be composed of all the following components except, so there's mechanical, pressure, electric, and then pneumatic. So pick an answer. So the control system works with the mechanics of breathing. And the mechanics of breathing, we really don't think that much about it unless you can't breathe or you can't breathe well. It's called the equation of motion is what we're going to talk about. And this is the equation of motion for the respiratory system. And basically what the equation of motion looks at, it looks again at your compliance and your resistance. How much do you have to overcome? If there's good compliance and there's no resistance, your work is very, very low. If you have a decreased compliance, your work is going to increase. It's going to take more pressure to put the gas into the airways and inflate the lungs. If your resistance is really high, that's another place where you're going to go ahead and have to use more pressure to put the gas into the patient's lungs, okay? When you look at this formula, you can see a little bit with it that we have to look at the pressure for the ventilator plus the pressure from the muscles, which is equal to actually your okay. When we look at this formula, we're looking at, again, the pressure of the ventilator plus the pressure of the muscles that have to be overcome. And we're also looking at the elastance in the lungs that have to be overcome. This is your elastance times your change in lung volume plus the resistance times the flow it takes to deliver this gas to the patient. So when people talk about mechanics of breathing, one of the things you'll see in all of the literature, it's in your Egan's, it's in Wilkins, the rest of your resources at this particular point, they're going to talk about the equation of motion, and that's what we use to go ahead and deliver breaths. There you see your lungs. These are pretty good compliant lungs. So the formula for elastance is pressure over volume. It's a change of pressure over change of volume. Resistance is pressure over flow. Elastance plus resistance is the impedance or load against your pressure coming out of the ventilators plus the pressure of your muscles. And that, again, as we talked about, this in fact is your equation of motion. Your mechanical vent, we don't use elastance, we use compliance. And compliance is a change in volume over a change in pressure. And the reason we do that is because we're measuring the compliance of the lung. How compliant is this lung? We know that if the lung is fairly stiff, it's going to take us a lot of pressure to be able to push the gas in. Sometimes if we run into a lot of decreased compliance, this may be a time when your physician says to you, let's go ahead and switch this patient to pressure ventilation. If you remember, the definition of pressure ventilation is that the pressure is constant. However, the flow and the volume vary, and they vary with that compliance and that resistance at that particular point. And so in this case, in order to protect the lungs, we'll sometimes use pressure ventilation to go ahead and do that, okay? Elastance isn't going to do very much for us, but we do need to know what we're working against, and that's your compliance. So the formulas, as you can see here, and we're going to talk a little bit more about these later on. Compliance, any type of compliance you're going to talk about is volume over pressure. We're going to talk about what we call tubing compliance. We're going to talk about static compliance. We're going to talk about dynamic compliance. And guess what? The formula is always going to be volume over pressure, volume over pressure. Your peak pressure is in volume ventilation, the maximum amount of pressure it's taking to deliver the gas to the lungs. Why did I say it's your pressure, maximum pressure in volume ventilation? It's because remember, volume ventilation, the volume is constant, the pressure varies. When you set a patient up on pressure control, you set that peak pressure, okay? This is the maximum amount of pressure you're going to allow the patient to have at that particular point per breath. In volume ventilation, the peak pressure is the maximum amount of pressure it's going to take to deliver that gas to that patient. And if you notice, the two parts of it are airway resistance and lung compliance. Airway resistance, it's your pressure. We're going to talk about your peak pressure, and we're going to talk about plateau pressure. And if you notice, we subtract PEEP from all of these before we do anything else. And the reason we subtract PEEP is that artificially elevated baseline above the zero baseline. If we try to do the math with PEEP in it, we're not going to get the right numbers. We're going to get some really way out in left field type numbers. So what we need to do is remove the PEEP and put the pressure back at the zero baseline. So airway resistance is your pressure, which is your peak pressure minus your PEEP, minus the plateau pressure minus the PEEP. These are two different pressures that we measure. That's why PEEP has to be taken off of both of those. Divided by your flow in liters per minute, divided by 60 seconds per minute, okay? So what happens is when you have the answer for airway resistance, it's always centimeters of water pressure per liter per second, okay? Lung compliance, again, it is always volume over pressure, a change in volume over a change in pressure. This is it. Ugh. Waveform conventions, for the most part, we used to follow these. Well, we don't do that necessarily, but if anybody should ever ask you, this is what you're looking at. How do we present these waveforms? Now with the newer ventilators, we can present our waveforms any way that we want to. But as you can see here, the waveforms we talked about are pressure, volume, flow. As a result of that, guess what? Everything is pressure, volume, flow. And they're all plotted as a function of time. When you look at the waveform, you're going to see your time at the bottom of the waveform. Remember when we talked about the waveforms before, what we're looking at when we're trying to figure out the total cycle time, when we're looking at the respiratory rate, we're going to take the time that we see the breath starting. We'll watch that and see if that time stays the same. And if it does, then we know that that's how the breaths are going to be determined. That's also how the total cycle time is going to be determined. And like I said at the beginning of this, if you wanted to, you can go ahead and just draw a line, put 0 at the end. That's your baseline, 0 baseline, and say, okay, the patient has a respiratory rate of 12 breaths per minute. 60 divided by 12 is 5 seconds. My total cycle time has to be 5 seconds. And so what I need to do is, if I'm drawing this timeline, I have 0 at the end, 5, 10, 15, 20. And then just put an X at that 5, at that 10, at that 15, at that 20. And in between the 5 and 10, there's your total cycle time. Remember, total cycle time is made up of inspiratory time, expiratory time. Inspiratory time varies, just depends on how long it's going to take to deliver the breath to the patient. Expiratory time picks up what's ever left over. Remember too, we talk anything above the baseline is positive. When we add PEEP, anything now between the PEEP level and the zero baseline is considered to be negative because it's below the new baseline. The new artificially elevated baseline when we have PEEP is your level of PEEP. And so when we drag the PEEP up, say from 0 to 5 centimeters of water pressure, if we have a sensitivity, pressure sensitivity of -2, we drag that -2 from below the zero baseline and bring it up so it sits below the PEEP baseline. And in this case, because you have a 5 of PEEP, 5 minus 2 is 3, we will see the PEEP, the sensitivity level at a 3 centimeters of water pressure. Okay? Easy, just go with the flow. Just remember, anything above baseline is positive. Anything below the baseline has to be negative. On the vertical axis, we see centimeters of water pressure for the pressure waveform. We see mLs for the volume waveform, and then we see liters per minute for flow. And then on the bottom, as we just got through talking about, this is always time. And everything that's happening to this patient is being done over time. Okay? When we look at the different waveforms, the only waveform that purposely goes below baseline is your flow waveform. You'll see the gas that's being sent off to the patient. It starts when the breath starts. Eventually, just depending on the inspiratory waveform, it will go ahead and stop and will begin to come back down at that point. Then what will happen with it, once the gas flow stops, the inspiration ends at that point, it will go back to baseline and will continue below the baseline because now you're exhaling. Once you finish with your exhalation, that waveform is going to come back up to the baseline and it's going to wait for the next breath to start. So it is a waveform that actually purposely goes below the baseline. Now you may be asking then, well, how do I know it's flow versus a patient-initiated breath? Well, the flow has more flow below the baseline than the patient-initiated breath has in sensitivity. And we'll see a different type of waveform from the patient than we'll see from the flow waveform, okay? So if you look at the picture here, this is from one of the ventilators. Looks like the Puritan Bennett 980. You can see that you have the airway pressure. PAW is airway pressure, measured in centimeters of water pressure. And you see that you have a red portion to this waveform, and then you have that bluish green portion of it. The red is the inspiration, the bluish green is the expiration. Okay. If you look on the next one, it says flow in liters per minute, and you can see that the breath is being delivered again. Inhalation is red. Once the flow stopped, this is called the square wave. Then we went ahead and started exhalation, and if you notice, the exhalation went below baseline at that particular point. And then it came back up to be ready for the next breath in inhalation at that point. The bottom waveform is your tidal volume in mLs. Same thing, the red portion is the inspiratory portion of it. This is the inspiratory time. Anything in that greenish area, that is your expiratory time. And if you notice, both the pressure and the volume waveforms do not go below baseline. So there's no patient-initiated breaths here. What mode is this patient on? I don't have that at this particular point. But remember, if your patient, oh, there it is, volume AC. But if your patient is on SIMV or IMV and they're not breathing, it's going to look just like this, okay? So this particular screen is telling us this patient's on volume control, assist control is the mode for you. If you look at the top waveform, which is your airway pressure, you'll notice that the line is a little bit above the baseline. That's your PEEP, okay? And if you look off to the side a little bit, let me see if I can get this to work. I colored at this point. This is your PEEP of 5 centimeters of water pressure. And if we look up here, we can see there's your 5 centimeters of water pressure at that particular point. Okay? If you notice, both the flow waveform and the volume waveforms start on the zero baseline. Okay? So if we were to come in here and we were to see that this was more elevated, and it's telling you your PEEP is supposed to be at 5, but now we look at it, we notice it's much higher than 5, and we see this waveform, the flow waveform, going down, and instead of coming back to baseline, stays down here, then we would be able to look at auto PEEP at that particular point in time. Auto PEEP will show up best on the flow waveform, second best on the pressure waveform, and we're not going to see it with the volume waveform. Okay. So control variables. Control variables are the variables that are going to manipulate the machine to cause inspiration. And there's mainly 3 variables, and they're pressure, volume, flow. So remember, pressure, volume, flow are the variables that we have for our waveforms. Their pressure, volume, flow are the variables we use for practically everything you're going to see. Now the question comes up then, well, where does time fit into this? Time is always there. If pressure, volume, flow is doing nothing to deliver a breath to a patient, then the variable is time. So time always sits there, and time continues to move, okay? So only one of these variables, pressure, volume, flow, or time, can actually be in control. That's where the definition of pressure ventilation, pressure constant, volume varies, volume ventilation, volume constant, pressure varies, comes into it. That's what you need to remember. And volume is integral of flow. There it is. Flow times time gives us volume. We're actually going to measure it. The machine measures it for us, so we know about how much volume is actually being delivered. What we're looking at with this too is we're going to go back to look at resistance and compliance, and that's part of your equation of motion at that particular point. So there it is, pressure controller. The ventilator controls the pressure, volume, and the flow vary with compliance and resistance. How do we know that? Because when we go in and look at the waveform, if the patient starts coughing, biting on their tube, have secretions coming out of their mouth, which happens quite a bit, and they're starting to cough a little bit and become very restless, the pressure is going to stay the same. We're going to see the differences with the volume and the flow. The pressure waveform, for the most part, we show a square or constant flow during inspiration. And basically, it's kind of hard sometimes to describe it. How I describe constant flow is the gas is going to be pushed out. And once the gas stays, it's going to stay where it is until it's time to end inspiration. So it's all at once. When we look at this with our balloons that we use or our test lungs that we use, you'll see that when the gas is delivered, it's like we're open at that point. That's your pressure waveform, okay? Remember too, as we said, pressure really was some of the first things we started to use when it came to mechanical ventilation. And it was not till a little bit later that we actually got into volume ventilation. Remember, we still use pressure a lot of times with the babies. We also use volume with the babies now. We also use a lot of pressure with our adults. and we also still use volume with our adults. It's just a matter of who's running the vent at that particular point in time. Negative pressure, this is your iron lung. This is your caress. This is your poncho. There's a new one, a biphasic negative pressure out there also that can be used. It is pressure. So here's another example of pressure controlled ventilation. The changing ventilator settings, the effective time at this particular point. You can see up here, you have an infection difference at this particular point. But you can see, if you notice the difference between these, the flow ends about this time, then it comes down for exhalation. It does the same little bit on the second one, but on the third one, it says it's not quite as much, and you can see the waveform. In fact, it actually did change. This exhalation is away from that beginning of the flow waveform. When we look down here, here's your pressure, and regardless of what's happening to these pressure, look at all these pressure breaths. They're all the same height. Because of this means the pressure is in control. When you look down here, you can see here's the volume. But as you go across, that volume goes up a little bit here. We see a difference with the volume up at this area. And then over here, we see the volume a little bit higher at this point. Because the volume and the flow are changing, this has to be pressure control. So volume and flow controllers, this is where your volume is constant, your pressure varies. You can see the pressure, again, is going to be varying with compliance and resistance. The flow is also going to be constant. And so there you see it, a flow controller. The ventilator controls volume. Remember, how do we know that the patient's volume is even in control? We're actually measuring the volume the patient's receiving. But we're going to see a change with the pressure at this particular point. So this is a picture with a volume controlled ventilation. Again, there's constant flow, which is the square inspiratory waveform. If you can see the set tidal volume and flow, your airway pressure, and it's telling you right here, airway pressure, which is your PAW, will increase with tidal volume, flow, decreased compliance, increased resistance. Compliance and resistance are opposite of each other. If your compliance is going down and you have problems with resistance, resistance is going up. Doesn't necessarily mean it's going to happen all the time. The problem may just be compliance and not resistance, or the problem may be just resistance and not compliance. Okay? It's also going to decrease with an increase of the patient's effort because the patient is, not putting that much into it. So it just depends on what's going on with that patient. Okay. If you look in Egan's, and you can also look in Pilbeam, you'll see these little graphic charts as you go across. And what you're basically doing, it's going to tell you, how do I know who's in control? And so what you do is you just basically start answering the question. The first question in this case is, does the pressure waveform change with changes in the patient's lung characteristics? If the answer is yes, then you need to go to the next one. Does the volume waveform change with changes in the patient's lung characteristics? If the answer is yes, then this one you go over here, the ventilator maintains or controls the time. In this case, this is a time controller. That's what's controlling it. Back on the first one, when you ask that question, if the answer was no, then the ventilator is going to maintain or control the pressure waveform. Excuse me, and as a result of that, this is a pressure controller. If you've gone through the next one down here, is the volume measured and used for determining the volume waveform? If the answer is yes, the ventilator maintains or controls the volume waveform. There's your volume controller. If the answer is no, the ventilator maintains or controls the waveform, it's now a flow control. So if you look at these, you can see Robert Chatburn at the bottom. He's the one who actually sat down, and he's the one who came up with classifying vents according to pressure, volume, flow, and time. And one of the comments that was made at one time is that he's probably going to have to go back and redo this because of the pressure ventilation, different modes that we're talking about now. So one of the things that you guys defined on word list 4 were phase variables, okay? And phase variables, believe it or not, are the results of pressure, volume, flow, and time. I know you've heard that before, so it's always nice to know if anybody should ask you, what's going on. You can just tell them basically pressure, volume, flow, and time is what's happening. One ventilatory cycle has 4 phases. This is what the machine has to do with your patient when they're helping them breathe or giving them the breath. It has to initiate inspiration. There has to be a way to say expiration is over. It's now time to start inspiration. It has to deliver whatever the variable is. Is the variable flow, volume, or pressure? Let's take a look at it and see what it is. It then has to end inspiration because you've reached the parameter. Once we set a variable and a parameter at this particular point, you cannot exceed it. If you're delivering a tidal volume of 350 mLs, if you hit 350 mLs, that's the end of the flow. That's the end of the inspiration at that particular point. You cannot go to 375. You cannot go to 400 if you're in volume control. And then the last one, it has to allow expiration. It has to be able to figure out where is this expiration going. Most of the time when we do expiration, it's pressure, and it's going to be either PEEP or zero, which is called zero pressure at that particular point. When we talk about these phase variables, we talk about trigger, limit. Egan's has added target to it also, which is limit, cycle, and baseline. Now, a lot of times with the students, when we talk about cycle, people go, well, a cycle must mean the entire thing. It's cycling from one breath to the next. Yes, that's a different definition of cycle. When we talk about the phase variables, though, that is not the definition of cycle. So you need to know, what are you talking about at that particular point in time? So for the most part, trigger, and there you see there's a little trigger with the pony. The trigger can either be time or patient, okay? If it's not pressure triggered, flow triggered, volume triggered, then it had to be time triggered at that particular point. And remember, if it's pressure or flow, it's a sensitivity that we set to allow that patient to go ahead and initiate that machine breath. If the machine initiates the breath, then it's a time. Remember, how we get the time is based on the respiratory rate. Again, if your respiratory rate is 12 breaths per minute, every 5 seconds the machine is going to initiate a breath for you. Remember that 5 seconds to the next 5 seconds is your total cycle time, and it has to have TI and TE in it at that particular point. When you're using pressure ventilation, a lot of times your time is being preset for you. You can set it as I time, and sometimes they'll set it as the I to E ratio. You're going to see that quite a bit in nursery, okay? You'll see it with some of the time with adults, but at this particular point where you're going to see it quite a bit is in nursery. Again, remember, when time is going on with your sys control or your IMV, the breath really doesn't care what's going on with that patient. They don't care if they're in the process of inhaling, exhaling. If it's time to deliver the machine breath, the machine will step on or breath stack that breath on top of the patient's breath. And so what we're going to look at is how do we know what the rate is, what happens to the IDE when we're working with those. The variable TITE is a result of compliance or resistance. Okay. The other thing we have is also a manual inspiration button. And people go, well, why would you have a manual inspiration button? Well, here's sort of an off definition of it, okay? If you have a patient who has a respiratory rate of 2, and we have physicians who sometimes give you a respiratory rate of 2, that is a 30-second total cycle time. And if you want to listen to this patient, that means, and you want to know how they sound with the machine breath, that means you've got to wait your 30 seconds, if you haven't caught it at the beginning of the first breath, to be able to catch those breath sounds at the second breath. So by giving that manual inspiration, which is not going to bother the patient, then we can listen to those breath sounds. The other reason we would do this, if you're going to record cuff pressure has to be done at end inspiration on a machine breath. Cuff pressure is measured at end inspiration on a machine breath. If you're sitting there going, well, what happens to cuff pressure on CPAP or spontaneous? We don't worry about it because the patient is breathing spontaneously. They're setting their own pressure. What we're trying to figure out is how much pressure is the machine using at this particular point in time. So all of these are done on machine breaths. So here's part of that same thing we talked about, the controller. Now the question is, does inspiration start because a preset pressure is detected? If yes, then inspiration is pressure triggered. This is a pressure sensitivity. Remember, your book tells you pressure sensitivity is between negative 0.5 to negative 1.5 centimeters of water pressure. A lot of times when you go out to the hospital, you're going to see that they actually use -2. However, you may also see it set much higher if that patient is starting to do what we call auto trigger, that they keep hitting sensitivity and the sensitivity is set too high at that point, or not too high, then every time they either cough, or we see this also with hiccuping, the machine's going to deliver a breath to them. And so to stop that, we're going to drop that sensitivity down even more. If the answer for this is no, then does it start because a preset volume is detected? If the answer is yes, inspiration then is volume triggered. If the answer is no, does inspiration start because a preset flow is detected? This is your flow by. If the answer is yes, inspiration is flow triggered. If the answer is no, it starts because a preset time interval elapsed. Therefore, inspiration is time triggered. Okay. So looking at this, we're going to look at this as a patient trigger. Remember, the patient has to hit sensitivity in order to be able to tell the machine that they want a breath. The machine senses the patient's inspiratory effort. If they hit the sensitivity level, then the machine is going to go ahead and release the gas to the patient. Remember what flow by, there's already some gas in the circuit. There's a lot of synchrony going on at that point, but the demand valves still have to release the rest of the gas. Remember, those demand valves are really sensitive and they're ready to go ahead and deliver their gas. You can either measure sensitivity with pressure, volume, or flow. The two that we most commonly use are going to be pressure or flow. Pressure, there's your sensitivity again, negative 0.5 to negative 1.5 centimeters of water pressure below baseline. and the flow is available in the circuit. So we're going to pull out. Remember, we're measuring how much flow is in that circuit, and as long as that flow has gone down enough, then we're ready to give that patient a breath. If the response time for your demand valves is not responsive, though, what we're going to see is asynchrony or dyssynchrony and increased work of breathing. That's part of the reason why the vent manufacturers now have flow-by in the circuit, because it makes it so much better that we can keep these guys in sync with the ventilators. Limit or target. This is the variable reached held before inspiration ends. The definition of limit is you do not terminate inspiration. Because you do not terminate inspiration, time cannot be used as a limit, because if you hit time, it has to end. So what happens is we hit wherever the parameter is, and if it's not time to go ahead and exhale, the machine is going to hold that parameter until that time comes around. We see that more often with pressure than we do with volume. You can sometimes see it on the vent because you'll see the waveform going on, the graphic going on, and as the graphic is going on, then you'll see the termination at that particular point. Pressure is going to limit the amount of peak inspiratory pressure. Peak inspiratory pressure is the amount of pressure it's taking to deliver that breath. Remember, with pressure ventilation, we set the peak inspiratory pressure. Volume limits the tidal volume. If the tidal volume is set at 350 mLs, 350 mLs is delivered. That's the end of the flow. It's going to be held there until it's time to end the breath. And then flow will limit the amount of flow that we also give during inspiration. And again, we have that chart. And like I said, this chart is in Egan's. The chart's also in Pilbeam's. Same question. Does peak pressure reach peak preset value before inspiration ends? If the answer is yes, it's pressure limited. If not, let's go take a look. Does it reach the value before inspiration ends, the volume? If the answer for the volume is yes, then inspiration is volume limited. If the answer is no, then we're going to go across and say, does peak flow reach peak preset value? If so, it's flow limited. If the answer is no, there are no variables limited during inspiration. And that would be something that would be open and something we don't have to worry about. Cycle, this is when the preset value has been reached and time has passed, okay? And so what we do is the inspiratory phase is going to end when the value is reached. Your cycle can again be pressure, volume, flow, time in this case, or manual. If you do a manual breath, as soon as you let up on that little thing that you're pushing down, the breath cycles off, okay? One of the things we're going to talk quite a bit about, as you can see with volume, the measured volume from the output control valve does not equal the volume delivered to the patient. This is where we're going to talk a little bit about tubing compliance. You're going to have folks who tell you, don't worry about tubing compliance, not a big deal. I'm going to tell you, it's still a big deal. You need to know how to figure it. When we're using some of the pneumatic ventilators from Fortran or the transport vents, you need to know that because you have to be able to set your volume to make sure the patient gets the volume that they need. So when we talk about compliance and resistance, we're going to talk about this type of compliance. And as you can see, it's a volume that's lost in the compression of the circuit. Okay, it's called compressibility at this point. So then we see our graphic again. Same questions. Does expiratory flow start because a preset pressure is met? If so, your inspiration's pressure cycle. If not, Does it start because you reached a preset volume? If yes, it's volume cycled. If no, it's because it could be flow. So the question is, does expiratory flow start because you hit preset flow? If the answer is yes, then it's flow cycled. If the answer is no, it's because you reached a preset time and the interval has elapsed at that point. What you want to be aware of is because on our ventilators, if I have a pressure trigger, I don't have to have a pressure limit and I don't have to have a pressure cycle. If I have a volume control, I'm going to control whatever the volume is being delivered, but I don't necessarily have to have a volume cycle at that particular point. So we can use different things when we're setting up the ventilator. We can use a pressure trigger, we can use a volume limit, we can use a flow cycled, and then we're just going to go ahead and exhale. So it's a matter of how do we set up these vents. And then baseline, for the most part, this is controlled during exhalation. Pressure is most practical, as you can see. It's always measured and set relative to atmospheric pressure, or zero, and that's called ZEEP. So if anybody ever asks you what is ZEEP, zero in expiratory pressure, it's atmospheric pressure. PEEP, again, always set above the baseline. NEEP is set below the baseline. We had some IPPB machines that actually had NEEP on them, and NEEP is not wonderful, so we just ignore that. So if you look in your book, you'll see this chart, and this chart has everything on it. There's your trigger, your limit, your cycle at that particular point. Okay. And here you have it. All the following are baseline variables except ZEEP, MEEP, PEEP, or NEEP. Okay. So this is where we're going to stop for today, and then we're going to go into the conditional variables later. Like I said, during this week too, we're going to go ahead and do compliance and resistance. We're going to talk about the different formulas that go with it. That may take a day or two to be able to do that. That is not a problem, but it'll explain a lot of the information that we've seen on the slides today too. Your assignment for today, I'm going to post it to course content. Most of it's going to be a multiple choice, and it should be kind of an interesting one.